So, hello everybody from Bonn. I'm really happy to be here today, even we are the last one, so we hope that you can enjoy with our challenge. For me, it has been a pleasure to mentor this challenge together with my colleague Eddie, Julie, James, and Melanie. And yes, thank you very much to the team members and congratulations to arrive to this stage. We are quite happy with the solution that you have provided for this challenge. And the team members are Irma, Sergio, John, Jonas, and Xavi. So please, next slide. So the motivation for this challenge just was born in the framework of the Copernicus Energy Hub. That is a new initiative of the European Commission implemented by ECNWF, which main objective is to illustrate and facilitate the uptake of the Copernicus data, but also the information that is relevant for the energy sector. So till now, in the Energy Hub, it's possible to access to the different data sets coming from different Copernicus services, but it's not possible to visualize or making comparison from the different data sets. So then we just put an idea over the table and we just put the challenge up to create a prototype web application that allows to visualize and making comparison of data set coming from CITRIET and from CAMS, two of the ECNWF Copernicus services, and put it together in an application that can allow to the solar energy sector to visualize them, but also to have a feeling just before downloading this data. And yeah, this is the challenge, and I think the teams have done very well. So I hand over to Sergio to continue with the presentation. Thank you very much.
Thank you, Nube, for introducing the team, the mentors, and the motivation behind this challenge, the SunVizor project. Here we have the agenda for today's presentation. First of all, I will introduce the project description, the objectives, and the variable selected. Then John will conduct a live demo to show SunVizor capabilities and to show the functions that we have there. Afterward, Irma will deep dive into the methodology, and then Jonander will explain the architecture and the feature work. So next slide, please. Okay. The objective of this project is, as Nube has said, create an interactive and user-centric web application for end users to effectively visualize the data related to energy sector, basically solar sector, from different AC MWF catalogs, C3, ANS, and CAMS, and visualize the data at different time scales, such as historical data, next day's data, and climatic projections. The objectives here for us is provide the renewable energy sector with a new layer of value regarding weather data access and visualization. As we work in the sector, we consider that is a need for our sector, as well as collaborating with ACMWF in this project and get along with all the data in the different catalogs. And of course, enhance our team's data visualization skills. So if we go to the next slide, before moving to the main findings, I would like to explain a little bit the variables that we have selected to visualize in the SunVizor. The ones highlighted in blue are the ones that we are going to see later, and the ones in gray were in the roadmap, but for different reasons, they are still not there. So from Era 5, we have 2-meter temperature, surface solar radiation downwards, and snow depth. From climate and energy indicators, we have surface downwelling shortwave radiation, solar photovoltaic power generation, and also 2-meter temperature. And from CAMS, we have global horizontal all-sky irradiation and clear sky irradiation. For this proof of concept, we have downloaded 5 years for each variable, and we expanded the bounds that we have initially, and it covers especially almost all Western Europe. So having said that, I will hand over to John that will demo the SunVizor application. So John, the floor is yours.
Hello, everyone. So I'm going to show you the application that we developed. So the first step that I want to show you, we had an API. In this API, we had 2 principal endpoints. The first endpoint is to retrieve the whole structure of the variable that Sergio mentioned. So in this structure, we get the name, unit, icon, aggregation, the models that we are going to use in the user interface. And the second endpoint, that this is the important endpoint. Here we have the all information that we pre-processed and with the aggregation that we selected for. In this case, this is an example for the temperature, as you can see here, and this comes from the ERA5. And we are using aggregation only, and this is the value. So this is very interesting for the user because we are offering the possibility to download the flat data directly if they don't want to use any user interface. So now let's move on to the user interface. So, okay. As you can see here, this is the area that we selected to show all the data. We include some nice functionality for the first user. For example, we include a short tour guide for the user that inside the first time in the web application. So as you can see here, we indicate the user, select the variable, choose a point in the map, and finally we can see the results in this slide that we are going to show you in a few moments. So for this example, I'm going to show you to select temperature. And for example, I'm going to press here in Paris. And as you can see here in this window, we have the location that we selected, the models where we are getting the information, and the aggregation that we selected by default. Here, the user had the possibility to change the option, and we offering a short description of the aggregation that we are offering. So in this case, we had monthly, but if we want yearly, we had this possibility also by month. Another important thing here is that we are offering also the user the possibility to download the data directly in CSV file. So in this case, for the temperature, for example, in Paris.
Yeah. So, for example, let's say that you are a user who's interested in solar data to build your solar plant. So in this case, this variable is very important because the temperature affects the efficiency of your panels. So in this case, you can compare between this point and another point. Please, John.
So this is the other important functionality
that
we add.
Yeah, this is one of the key features of this application. You can compare between different points. So in this example, you could find a better place with better temperatures for install your panels. And you can select 4 points.
Yeah. For example,
at maximum.
Spain and here to see the difference.
Yeah. We can compare the difference between the 4 points. So, for example, we can now select another variable. For example, if we are interested in one of the radiation variables, which are very important for the solar sector, Let's say, for example, now let's again select new points. Let's say that we want to build a plant in Reading.
So
Okay.
here.
Now we think also that a good place is Bonn and Bologna, for example. Okay.
And why not Spain?
Okay. Okay. So here you can clearly see a difference. So for this user, it's very easy to compare between these 4 points and to have a better decision of the place where he wants to build his solar plant. And also you have the option, if you see behind the plot, or below the plot, you have a slide, and you can zoom in your data to have a better view of the information. Yeah, and for example, we have different temporal aggregations, as you see, daily, monthly, yearly, as John was mentioning. So for some variables, maybe you are interested in the daily time series, or for example, for radiation, I think it's very important by hour. You maybe want to check the best hours or something like that. So yeah, that's very good.
So, and finally, here in the website, you had a lot of a short summary of the documentation, and also in GitHub you have available of the information, the technical information. So now we are going to talk about how we did it, all this platform.
Okay, yeah. So yeah, thank you. So okay, so now that you have seen the Visor, let's better understand how it works and what's behind it. Okay, so as many of you know, the European Centre offers a wide range of meteorological and climatic data, but each data set can be accessed from different places and in a different way. So imagine that you are a user coming from the solar sector who doesn't know much about meteorology, but you need to access solar data. Well, I think in this case, the user would be a bit lost. And apart from this, there's also a challenge of downloading massive data sets like ERA5, which covers 80 years of data, because processing such a large amount of data, I think, can be overwhelming for the user. So what's our solution? We want to unify all this data. Okay, so the CDS and ADS service offer the option to download the data in netcdf and GRIP format. So for our project, we have decided to download the considered data in netcdf format, and then we apply pre-processing to calculate the different temporal aggregations, such as the daily average temperature or the cumulative rainfall per year. You can see here a list of the complete aggregations we have chosen. And now, and here comes, I think, one of the most groundbreaking parts of this work. We transform this data into a format called SAR. And this allows us to combine and organize data from multiple sources, reduce file sizes, and optimize access times, which is also very, very important. So to have an idea of what I'm saying, here's an example of a netcdf file compared with its SAR counterpart. So you can see in these plots that the SAR file is 40% smaller and offers also faster reading times. And I have to mention here that for this test, we have used only 5 years of data, but we have seen that the optimization increases as the volume of data grows, so it's very nice. So now, for this proof of concept here, we focus on a small region in Europe, downloading 5 years of data for the variables of the selected models. Here you have an example of a time series of the surface temperature for 1 point in that region with an hourly resolution. And then as I mentioned, we process and transform this data into SAR format. we mainly use Python with XRI, and then we store this data in a virtual machine so that the API can access to this data and display it in the web application. Okay, so now I think it's time for my colleague John to show you the architecture.
Thank you, Irma. Okay, now it's time to speak about the architecture. So we have developed 2 projects. The front-end one is a website that is developed with React and TypeScript, and it has HTML code. We have to mention that we are using Vite, and with Vite we can package all the libraries and launch it locally in less than a second. So it's easy to work with that technology. And for the charts, we are using the eCharts library. The other project that we have developed is the SunVizor API. It's a Python code. We are using the Fast API, the library, and there are developed 4 main endpoints. Here you can see the first one, there is /API and /variable, and the variable info. The first 2 are related only to show the variable information that we have preprocessed and we are offering through the website. And the other 2 endpoints, the API point and Solar data, are related through the data series. So also, in the server, we have a property file. As you can see here, each file is one variable with different properties. Here, for example, we can configure the conversion formula, for example, for the temperature. We are receiving in Kelvin, so we are converting it to Celsius degrees. Here, the technology for the reading files is XRI with SAR library. This is an example of the 2 variables, 2 endpoints that we showed before. Are in a JSON format, and the idea is to use the web for the normal users that they can navigate through the web and download the CSV files, and the other part for the developers, they could use directly the endpoint and use it for their developments. And here it's important to mention that in this property file, each variable that we configure here will be we have a repercussion in the website. All the website is dynamically loaded through the API, so all the information that is stored in the server will show here dynamically. So we can put a new variable or we can remove it without doing a new development. So continue with the current deployment structure in the server. We have a server in a European Center site, I think, and here to deploy the 2 web servers, and we only have the 80 port available. We have installed an Nginx working as a reverse proxy server. So here is a little configuration that you see in black. Now, when the user is giving new requests to this Nginx server, by default, all the requests will go to the web, except the ones that starts with /API. So inside, there are 2 applications running in localhost, and the engine is the gateway that will redirect all this information. And now we go to the future conclusions and future work, sorry. So we have put 4 main points. The first one, we thought maybe is the most important one, is focus in the data. Now, all the preprocessed data or on the downloaded data is stored now in this virtual machine. So, for the future, we think that it's important to separate in different layers the data, in one server or in different type of server. We think maybe data lake or something that this technology will be very interesting. Also, could be stored in a standalone servers or in an on-premise structure, but we think that the data should be separated with the applications. Also, in the data, we have to mention that we are using now SAR files, and this technology we are using by default configuration with little changes, but we know that if we delve deeper in the configuration of this technology, we will improve a lot the velocity to access the data and also the compression of this data. The second point, the web and API scalability. We know that if we will offer this data to hundreds of thousands of users, with one API, it will be impossible. So we will start to thinking to put this technology in an elastic cloud solution. There are many providers that offer on-demand services that if you have an increased demand, you can put new virtual machines, or if demand is zero, only to have one. So it will repercute in the cost of the solution. The third point regarding the DevOps and CI/CD pipelines, in this POC, we have developed and deployed all manually. So the next step will be to connect the code with the end resources, and also to take into account to have more than one environment: the prod for the clients and the development and quality for the internal developers. And the fourth step, the user management limits and cybersecurity. We also know that this API couldn't be open to all the users, so it would be nice to have an infrastructure that could have all the users authenticated and authorized. So also control all the requests that we receive, and put some limits in this kind of requests, or by user, or entire by all the server. And final aspect, cybersecurity. We don't have to forget this step. We know that to continue the good practices in this area is very important. So we would like to continue working in this area and to put all the needed security in different layers, starting from the starting requests and the security of the authentication of the users, and in the last part will be in the data lake part. And we know that if we implement all these features, so we know that the SunVizor project will be a product. So thank you.
Yeah, thank you very much, team. That was very interesting. I'm a geographer, so I could relate to a lot of aspects here. That was very interesting. Are there any questions from the audience? I know it's late and it's the last presentation. None. Do we have any online? Aging is not the best. So there are no questions online, but we will have the opportunity. We'll meet each other later, so I'm sure there are a couple of questions, and I will come up also with some. Thanks again to the team and to the mentors. Round of applause.
Thank you all.